Always a pleasure to be at UCLA. I started out at UCLA in 1968. I took physics in Knudsen Hall next door. I was in high school. Then I took all my math over here in the math sciences building. So I've been coming ever since here. It's really great. So I'd like to talk about a project that I've been working on for the past 7-8 years now. And this is the 2D materials. And so I got into 2D materials because I thought 2D sounded just right for me because I never figured out how to compute in 3D. But yeah, so, and it's turned into like an obsession. It's like the subject is just developing. And I'll highlight some of the things that have really exploded in the last 7 or 8 years in terms of research activity. Okay, so I'm going to present along the way work of many people, and they'll be listed in the papers I discuss. But the main new work is work due to Daniel Massett, who's a former student of mine, now a postdoc at the University of Chicago, will be starting at LSU in the fall, and Stephen Carr, who was a grad student at Harvard when I got to know him, and he's now a postdoc at Rutgers. So, okay, so I'm going to quickly go for maybe the first 20 minutes and talk about very elementary things about the Moiré scale, just because I think 90% of the people here actually don't know anything about this, I'm guessing. Okay, so I want to just tell you why it's become such an exciting subject. Okay, so let me start with the famous Hofstetter butterfly, which most people have seen. And this is kind of where the whole fractal business started. And this is just generated as an eigenvalue problem from Harper's equation. Now, Harper's equation is just a tight binding model for, say, some kind of square crystal. You assume some periodicity in this, say, y direction. And you have a parameter, which is a magnetic field that's transverse to the material. And so Hofstetter, he actually put this on a computer in the old days, which was very difficult. And he noticed this very strange structure. And if you kind of, it was very puzzling to people, so people didn't believe it, that you could change a little parameter in an equation and get such, seemingly it made rational and irrational numbers really make a difference, okay? So anyway, so this parameter B in this 3-term recursion relation is just a scaled magnetic field. A is the lattice spacing. B is the magnetic field. Phi naught is what's called the magnetic flux quantum, which occurs everywhere. And he states in his original paper, so at first glance, the idea seems out of the range of possibilities, since the rather generous lattice spacing of 2 angstroms demands a magnetic field of roughly 10 to the 9 G. Now, that's a magnetic field way beyond anything on Earth that people have developed in laboratories. And so what that means is that, okay, you can generate this beautiful picture from that equation, and it's all derived from a physical model, but you really experimentally can't probe this at all. You can only just probe a little teeny bit of this. So people tried to reproduce this in various physical systems, but not really in a crystal. So I want to tell you, that was first done in twisted bilayer graphene. So I have to tell you a little bit about graphene, which I'm mainly going to focus on in this talk, although everything I say applies to a whole wide range of 2D materials. So graphene, right, is just a hexagonal structure made of carbon. So you have, so both the red atoms and the blue atoms form triangular lattices. They're intertwined. We see so each unit cell contains what's called an A site and a B site. So so this is graphene. Okay, so and the thing is, if you put one hexagonal structure on another, at some small angle, then you get what you see is some pattern at a larger length scale, which really is just the beating of two nearby frequencies, which we're all familiar with, right? So this is just the beating. This is just the modulated wavelength. So you see this, and you could sort of understand this if you look at these different points. So let's say you move through the material, and let's say you focus on, you take a blue atom, and you say, okay, look at where you lie in this unit cell of the red atoms, right? And then you look at this vector, and you move around, then you will uniformly sample the unit cell of the other layer. Okay, so this is the Moiré scale, right, which is this Moiré envelope, really is just the difference, right, of the two wave numbers divided by 2. Okay, that's just, anyway, we all kind of know this kind of stuff. Okay, so so there was a very influential paper by Philip Kim and these other distinguished people. What they did is they observed that if you have one twisted layer on another, see these hexagons are the Moiré scale, and that acts like a unit cell for a much larger length scale. And so now let's say in this particular case, you have a length scale that's let's say 15.5 nanometer, as opposed to the length scale of carbon itself, which was 0.25 nanometer. So if you go back to that equation, so now you only need a much reduced magnetic field, and they actually measured this. Okay, they use density of states instead of eigenvalues, but literally they were able to probe the Hofstetter butterfly. So this is a kind of an early example of how the Moiré scale allows you to really do new physics. Okay, now so this field was very exciting. People were thinking, oh, if I put different 2D layers on top of each other and twist them at different angles, I can design designer 2D materials. Like I could replace silicon electronics by single layer electronics. It was a very exciting field. That's how it was when I was my first years in this field. But then a very dramatic experiment was motivated by the fact that at a special magic angle, okay, so if you say at about 1 degree, the band structure at the Fermi level, right, the level you fill the electrons at, is rather flat. Okay, look at this scale. This is really it's flat. So if the band structure is flat, right, then that means, then dE dk, partially respect to k for the band, right, that gives you your a very low kind of kinetic energy, which means, in fact, that the Coulomb interactions become important. So that means that correlated effects are really important, are really important in modeling the possible phenomena at this magic angle. And then, let me just skip to this. So what was really dramatic is the group of Pablo Herrero. They actually, they were able to detect a Mott insulator and a superconducting state, okay, at the magic angle. And what also is dramatic is that as you, what's really neat here is this is I was just trying to tell you this is just one hexagonal lattice slightly twisted on another, and this is the relaxed, when you want to construct the band structure, you really want to let the atoms mechanically relax. I'll talk about that. So this is really your unit cell. It's a gigantic unit cell, right, with all these with all the sublattices. And by appropriate gating of the material, you can say, okay, I'll have one electron in here, maybe 2, maybe 3, maybe 4, or I can go -1, -2, -3, -4. So that's just here. Here you see 4 bands times 2 spin, so you can go 4 to -4. And what's really exciting is you literally see these sharp changes as there's 1 electron per Moiré cell, 2 electron, 3 electron. So this kind of brings to mind an idea of like a periodic table. You can, just by simply turning on voltages, turning a knob, you can create really new materials, new electronic materials. And so anyway, so this was okay. So remember, in normal experiments, you have to kind of dope things. You have to put some, you have to change the alloy and dope it and whatnot. But here we're just turning a little knob. We're just turning a voltage. Okay. So you can explore all this new physics just by putting one layer on another and a slight twist. Okay. So that's. I'll come back to that. And I just wanted to kind of advertise.
Can I ask a question?
Yes.
Is for the band in the middle, what is the density of states there? I mean, are there many states, or is it just?
Oh yeah. That's also very important. Yes, of course. Yeah, very important. Okay. Now there's, and I want to advertise a recent work I did with Alex Watson, and that is looking at a simplified model. Which essentially, this model just essentially says the AA, it says, okay, this is the relaxed state. I kind of pretend this stuff doesn't exist, these little layers, and I get rid of that, and then I actually, we were able to prove, like rigorous proof, that the Fermi velocity, or the, which is just the derivative of the energy with respect to K, is actually 0. Okay, so we were able to do a rigorous proof of this, and then combined with a very influential paper by, we call it TKV, we're able to, that just shows that there really does exist perfectly flat magic bands in this so-called chiral model. Okay, so there. Okay, now let me just, okay, so let's just now, so I'm mainly going to talk about tight binding models, and let's just kind of remember that at 1 degree, you've got about 10,000 atoms in your unit cell, 60,000 electrons. So okay, so whether you could do anything ab initio with this, I mean, I think we have people saying they can do big problems, and let's be discussing. Okay, but more, I think what's actually going, a lot of what's going on is people just try to just model, right, the correlated of physics by these, going beyond the single particle to the 2 particle interactions. And so this is already, of course, as we've heard, a very difficult computational problem. Okay, so let's just kind of run through some of the 2D materials. Here's graphene, I already mentioned, hexagonal boron nitride, which is an insulator that's used all the time to encapsulate. Then you have semiconductors, black phosphorus, anisotropic. And okay, so here's me and my research group. We are starting out here. This is next door to the math department, my physics collaborator, Ke Wang. So he's kind of taught us how to exfoliate one layer. Okay, that means that's the famous Scotch tape. You put Scotch tape on graphene and just keep doing this. There's a nice video, How to Make Graphene, by one of my collaborators at Harvard. So type in How to Make Graphene Harvard with great music, okay? You'll see how to make graphene. But here we are, we're really doing it. We're really creating single layers. And then if you want to do these twisted things, you literally, what you have to do is you take a single layer, you cut it, and then you lift a little bit, and then you rotate and put it down again, okay? And the thing is, if you don't just take two materials from nowhere, then you're never going to be able to fit, because here you start, you know you're at zero, and there are all these little teeny mechanical gadgets. What's really neat about this subject is you can go next door and these guys can do amazing things, okay? Amazing control, you know, and so here, yeah, so we're you know, we're kind of, you know, assisting a little bit, you might say. Okay, and here's a little cartoon of a device of a, you know, 2D material. Anyway, what you can do here is you can vary stacking order of these. So you have only this whole, actually there are thousands of 2D materials. You can stack them in different orders. You can vary the Moiré unit cell by varying the twist angle. You can vary the filling of a unit cell, right, just by varying gate voltage. You can apply electric fields, magnetic fields, and in doing this, you can actually this is how my view, and I got this from Angel Rubio's paper, is I like this idea of a quantum simulator where you now have a huge space to explore all these phases, electronic phases that may only up till now exist as kind of theoretical conceptions, okay? So there's just, you know, there's a huge community just, you know, exploring all these things.
Mitch, what are these 3D flat bands? What's that?
I don't know. This is a project for a couple of years. There you go. Okay, and here's a few of the things that people have explored and experiment. Okay, this is just what this says. You take the top. You take a bottom is here's your graphene. Then you put a sandwich, twist it a little bit, and then you have another guy at the same angle. And that's actually very easy to do this, the band structure. And so people explored that. This is the bilayer in this, then you twist that. Then here's ABC trilayer graphene and hexagonal boron nitride. Here's twisted tungsten diselenide. So literally, there's like, again, 1,000 materials. People are exploring the whole, realm. It's much bigger than this periodic table of possibilities. Okay, so with that in mind, we started a project with my grad student, D.E. Lee and Stephen Carr. So like for me, this is my initiation into data science, is to try to use neural nets to, just from the band structure of an untwisted material, right? Can you predict in this case, local density of states? Can you predict the local density of states for the twisted material? So we've had some actually very good success in doing this. Okay. So let me now start with the more mathematical stuff.
I had a question.
Yes.
So how do you get your training data for that last one you showed?
Oh, we have like just a toy, 10 little toy models, and we're playing with parameters. It's all toy. Yeah. Okay. So here's here's our graphene again, and then the B1 and B2 are the reciprocal lattice vectors for the lattice vectors A1 and A2. Then actually this is the Brillouin zone. K and K prime are what are called Dirac points, which I'll explain their significance. Just to kind of fix some notation, which is not totally, it's kind of I'm using mostly a mathematical style notation rather than a physics notation. So yeah, anyway, so we denote lattices just by, AN is just an invertible 2x2 matrix. Here's the jth lattice, the jth unit cell. Again, each seat is periodic, of course. It's just a lattice, but the combined system need not be periodic. And then we can define multilattices just by attaching to each lattice point a set of orbitals, A1 here for layer 1, A2 for layer 2. We can define reciprocal lattices and then unit cell in reciprocal space. Okay, so now let me try to help you understand the notion of the Moiré and a little better. So one nice way to study Moiré is through the notion of disregistry, which is a concept from mechanics. So a disregistry means, okay, if you have two layers of something and how is the atoms on one layer, if it's just a crystal, and then everybody's in registry, but if you have some kind of defect or something, dislocation, then it may be slightly out of disregistry. So that just says that, so the disregistry of layer 1 with respect to layer 2 says each atom, say each blue atom, right, we project that into the unit cell of layer 2, and we get this kind of vector. So this defines disregistry at the lattice points of in layer 1, and similarly, of course, for disregistry of 2 with respect to 1. And then we can interpolate this to get a continuous function just by this formula. Okay, so we have, and then, okay, so we have that, we have isomorphisms. So here's as I said, the local configuration of an atom in layer 1 is defined by its projection up to the unit cell of layer 2 and vice versa. Okay, and now this is covered by our continuous disregistry by if I pull back the mapping, I get the Moiré. Okay, so gamma m is the Moiré, right? And so these are isomorphisms. So we can, in terms of the lattice vectors, the generating lattice vector, we can define the periodic Moiré cell, the Moiré superlattice, right? We can define it this way, and then we can define reciprocal Moiré lattice vectors. Okay, so as I mentioned, we use the tight binding models, and this is actually quite difficult to parameterize because if you just take a crystal, maybe like 2 or 3 numbers is all it takes, right? Because it's just you have one or two, an on-site hopping function, 2 or 3 nearest neighbor. That's all there is to it. But here, for an incommensurate material, the configuration is continuously varying. So you really need a function, you're to parameterize the hopping functions. Okay. So again, for each single layer, then the r minus r prime just takes values in the lattice. But in an incommensurate system, r minus r prime can take any real value in the real numbers. Okay. So then we have, so we define our Hamiltonian operator through the hopping functions, generates an eigenvalue problem. And the problem is we can't use block transform because we no longer have a periodic problem. Okay, so now I just kind of got this from a review article by Stephen Carr, and just kind of what they reported is they reported the results of just a DFT. They reported 3 million core hours to do this band structure. This is essentially I think it's the real space method that that I've kind of developed, and with relaxation, or maybe they might be using the low energy McDonald. They're probably doing that. And then this is this is our because empirical means the continuum model means this low energy McDonald model. And then this, according to Stephen, this is the method I'm going to give you, which is very fast and really gets the band gap. You need relaxation to get an actual band gap. Okay, so, all right. So let me just kind of run through. Yes?
So the previous band structure, so the K gammas, those are the Moiré uses, Yes,
these are Moiré. This is the Moiré scale. It's the Moiré wave vectors. Yeah. Yes. Very good. Yeah. So the most naive way to compute, so density of states or local density of states, right, which, I mean, so the density of states is the same as the local density of states in a crystal. All atoms are the same, but they're not the same in an incommensurate system. And there's a duality between a local density of states in real space and band structure, right, which is nothing other than a local density of states in momentum space. So I'm just going to introduce some of these concepts in the real space context. So here we just cut off our domain with some radius r. Then we have a projected Hamiltonian, and you could just go and diagonalize that. Now the problem with that is it's really bad because you have all these boundary effects. It actually converges only at one rate at scale 1 over r, where the methods that I'm going to show you are all exponentially convergent in in r, the cutoff of the truncation of the Hamiltonian. Okay, so the nice way. So from numerical point of view, actually, the best way to compute a density of states is to look at it as some kind of functional. Right, you essentially take the trace of g of h, where g is like a Gaussian centered at the energy you're interested in. You take the trace, normalize, et cetera. And so you could actually define an approximate density of states, right, through through this duality. Then you could define local density of states, right, just by taking these diagonal elements. Okay, so
some sort of ergodicity.
Yes, of course. Sure, I'll get to that. Yeah, absolutely. Okay, so now, because what you could do, so I said a bad way is just take some big circle and then just cut it off and do all your computation. A good way is to just try to sample each local configuration and get away with a much smaller radius, a much smaller problem. And then what we do is we go to each local configuration, compute compute the information around that state. And then we don't have any boundary effects if we do that. And so that's equivalent to, through ergodicity, instead of wandering all around, we can just sit there at one point and just shift the layers on top of each other. Okay, and that's what this B is, just some kind of shift. And then, okay, so that says that the local density of states at some lattice point R is just obtained by taking the projection, by looking at the disregistry of that and using that to shift. And then you can just, as you mentioned, use this ergodicity. And in the end, you get some nice integral, okay, which actually gives a proof that the density of states is a well-defined object in an incommensurate system, which when we started this, that was kind of not known. Okay, we didn't know that. So actually, I think Daniel was visiting Christoph and learned about some locality methods, and that kind of started it. Okay, so then we use what's called kernel polynomial method. It's a Chebyshev method, very fast. We approximate those Gaussians by Chebyshev polynomials, and you just have recursion relations very fast. I don't want to get into that, but okay. So one thing I will notice here, the local density of states is rather smooth, generally. Here's different angles. Here we compute the different disregistries, which we call AA means the A on one layer is on top of an A on the other layer. This means A on top layers on top of B in the other layer. And these are actually just for visualization. They don't really represent they're like the density of local density that should be shifted up and down. And this is the real space kind of, this is the real space picture. And these dots are at the AA sites, okay? And this is the Moiré scale. And I will say, we published this paper 2017, and the localization, the high density of electrons at these AA sites, we see that at the magic angle. So that was already indication of something interesting, again, a year before the experiment, okay? Okay, now let's just talk about the relaxation. Okay, so if you just take, so this is just a little, you look at so you take, if one layer is sitting right on top of another, each carbon on top of each carbon, that's the worst. That's the high energy. And then if you just kind of shift this along, then you get to some kind of, the minimum is if half of the carbon atoms are sitting in in the middle of the hexagon structure of the one below, that's good. So that's your local minimum. So you have an AB and a symmetric BA, you have a saddle point. So what you'd like is to be here or here, right? And so given an angle, and we've done this, we have a paper on this in archive, I don't know where, but so it's like, I guess you call it it's just a bistable system, okay? And so you have a competition, and you ended up with these domains with domain walls, and I'll talk about some of the estimates in a minute, but the main thing is, this is unrelaxed, relaxed. Now here's an assumption that is, we actually proved it in 1D, but it says that the displacement is a function of the local configuration, okay? So U1 is just displacement in the local configuration, and the displacement in real space is a function of the actual environment, okay? And this is really, in the 1D case, we explored this, and this is really dynamical systems. We use some fancy stuff with Aubry, Mather, kind of stuff with whole functions. So yeah, this is a very hard math problem if one could ever do this in 2D. But in any case, what this says is, since we know that dysregistries are periodic on the Moiré scale, that says that the displacements are periodic on the Moiré scale. We can actually write down an energy, on an elastic energy on the Moiré scale, okay? And now you might ask, okay, so this is their interlayer terms are just, linear elasticity, okay? That's fine. And then the more complicated stuff is the interlayer, and the interlayer is the energy of one layer not being how it's situated above the other, and that's something you can do with a small DFT computation, and that's what this is. This is graphene, where we study the energy of one layer shifted on another. You get we do it for zero angle. You get so you have a nice periodic problem, small unit cell, and you get these nice pictures. You can parameterize them with really 4 parameters with sines and cosines, and that's what we use, okay? So that's just this notion of generalized stacking fault energy. Okay, so now let me kind of try to motivate, flat bands. Okay, and these pictures come out of this paper that really shocked the world, the physics world at least, and that was again. Cal was the guy that was in the lab night and day, and Herrero is the advisor at MIT, and so these are from their paper, and so this just shows twisting one layer on another by angle theta. This shows the twisting of the Brillouin zones, okay, and then this is the Brillouin zone of the Moiré actually, and then this shows the local density of states, and I showed you a picture of that, how it's highest at these AA points, okay? Now this is the band structure of graphene, which everybody should know, and these are the famous Dirac points where you have linear dispersion, and then this shows their model, their little toy model for pre-computation for where flat bands come. So W is the hybridization energy, and so this is just I'm just focusing on these Dirac points. All the action takes place here because the Fermi level is here. So if you just took two graphene, you twisted one, and they did not interact. This is your band structure, okay. And now if you add the hybridization, right? What you see is here this point shifts down, right? Because you're hybridizing here. And then eventually there's a balance between, so there's 2 parameters. One is the twist angle gives this distance, right? There's a distance from this intersection point down to the Fermi level. And what you want to do is you want to take, and people have a good idea of what the hybridization energy is. They say it's independent of angle. And then you just want to change the angle so that in fact, the hybridization is enough to merge this point and that point, okay? That's the toy model. But of course, what we really need is a mathematical model, and that says, and so there we use the block transform, right, on the coupled system. Here's the real space model, right, with our hopping functions. Here's our bilayer wave function. We define block transforms, and then if you didn't have any interlayer interaction, it would simply be two periodic problems, and you could diagonalize each of them. That's just what this is. But then there's actually a very beautiful result due to the Poisson summation formula that says the scattering from one layer to another has this beautiful structure of just adding. Okay, it says that if you want to know which wave numbers of layer K, say, interact with wave numbers of layer. Actually, my next slide explains all that. Okay, so here you go. Here's our Hamiltonian transform to momentum space, and so then it says that this the block wave of wave number Q on layer J scatters to the layer K. It scatters to Q plus Gj, where Gj is in the reciprocal lattice space of layer J. Okay, but now we know this. We know the block waves are independent of reciprocal lattice vectors in layer K. So we have this kind of scattering, and we can use that to develop a very nice numerical method. Okay, so it's not just there isn't just chaos here. There's a beautiful structure in the scattering. Okay, so yeah. Okay, so now here's another. Okay, so what I started off saying, okay, here's a real space Hamiltonian. We can also define the wave functions in terms of configuration space. There's a total duality to, first we go to momentum space. We did that with the block transform. But then we could also do another duality to the reciprocal lattice space because, say, in the case of, because of this ergodicity, if you take all these reciprocal lattice vectors in layer 2, and then you project them onto the unit cells in reciprocal space, the Brillouin zones of layer 1, then you can actually represent those waves by either the wave number Q1 or the reciprocal lattice vector in the other space. This is sort of the relation. So that means we have a whole new problem that says, okay, if you want to describe the degrees of freedom on layer J, it's actually the reciprocal lattice space of the other layer, across its orbitals, and you can define literally a Hamiltonian in reciprocal space. Okay, and this Hamiltonian is just totally equivalent to the real space. Okay, except it has very nice, much nicer properties because because the single layers had band structure. Okay, it means okay, so that's now. Okay, so then we could, and I talked about that B shift. You can do what takes the place of B, this registry in real space, is Q in momentum space. Okay, so you can define. So now we have a fully equivalent problem posed in reciprocal lattice space with shifts. Okay, and this is right. This is exactly how you define that Hamiltonian. Okay, and all the properties are the same. So you have, and so here's a little picture actually that Daniel created showing you this kind of duality. Right, this is configuration space. Just says, okay, well, here's your layers, right, and then R1 and R2, and R1 corresponds to configurations by projecting onto the unit cell of layer 2. So you have this duality, and then using block transforms, you totally can transform it to reciprocal space, okay, momentum space. Okay, so the idea of okay, so what you have is that here's momentum space, and these maybe I should go to this next. I go to a picture here. I got some nice. What did I have to that? Damn. Oh, here. Yeah. Okay. So what we want to do is here's those two. Here's those two. Here's the two the band structures of each layer. I mean, we really just want to focus on this energy region, okay? And then so that kind of puts us over here, targets over in the so this is a projection onto the onto the Brillouin zone, let's say of one of the layers, doesn't really matter. And then here it's a bigger picture, and then here we can then transform that to reciprocal lattice space, okay? So the idea is to, okay, so let me zip back here now. Okay, so we can, so what that means is we end up with exactly the same method in momentum space and real space, okay? Now, I haven't taken advantage of the fact that if I'm only interested in a certain energy region, which is, say, around those Dirac cones, then only certain parts of reciprocal space are relevant, okay? So we actually literally can truncate our matrix. We really only need to look at much smaller problems. So if we do that,
Can I ask?
yes.
The previous one, you have this honeycomb, like shaded region. Do they correspond to the two valleys?
Yes.
Include all the two?
Yeah. So this is just the reciprocal lattice vectors of both of 1 and 2, both, and you see the Moiré structure. So this is like 1 corresponds to 1K valley, and this is 1K prime. But what's happening, just like in real space, the lattice vectors are kind of being modulated in the back to configuration. This is just the same as this, except it's a slightly different, corresponds to a slightly different K. Okay, because you're okay. So
yeah. So my question is that some physicists say that the coupling between the two values they are weak.
They are weak.
They consider like a single value model. Does this analysis shed some light on a more quantitative version of this statement?
Well, sort of, yeah, because we actually, when we compute, say, band structure or anything, we actually compute here and here. Okay, you'll see. There's a picture I have of that. Okay, yeah, we actually sum. We have this matrix and that. We add this to that. Okay. Okay, so let me. Okay, so here's the. Here's a Gaussian, and so recall that what I really wanted to do was take the trace of these Gaussians applied to the Hamiltonian, and in real space we end up with this kind of error estimate, and so that's what that says is that the decay. This is in terms of R, those problems I'm solving right at each point in configuration space. So what this says, yeah, so it exponentially decays in R, right? And then we have some, constant gamma. But then we have this kappa, which is the energy window we're sampling with our Gaussian. And when we as we look for more accuracy, by looking at a narrower Gaussian, the rate of convergence degenerates tremendously. Whereas in this momentum space method, we actually don't have that issue, okay? And so to compare, so in fact, if you want to have comparable error, then in the real space and momentum space with our little cutouts, then that's really proportional to this kappa, the accuracy you're seeking, and this is just a graph demonstrating momentum space versus real space, different rates of convergence as we go for actually it's more CPU time. Okay, so now I want to switch to the real topic of my lecture, which is what's yeah, which I needed all that buildup. Okay, so this is the you know, I think I'm on time. Okay, so what you want to okay, so the new thing is this, how to do these things for relaxed systems, okay? And to do that, so the most, what you say is that all these terms, this is all real space, the hopping functions, right, these matrices need to account for the displacement, because it's all about distance between atoms, right? Or whatever, orbitals, right? It's all about that. So we have to replace R by R plus U1 of R, okay? And okay, so this is the you know, the interlayer terms, then these are your interlayer terms. Now let's go to the, so eventually we're gonna have what I call configuration dependent hopping functions. So here's the hopping function for layer 1, interlayer hopping layer 1, we have to modify the distance between atoms, and then we can write that as, okay, so here, what have I done? I've taken U1 of R and written it this way, right? So what that means is I can actually, I can define a new hopping function, H sub R, that is configuration dependent, and that's just defined this way. So that means that, so normally you just define a hopping function is just, you know, R, but now it needs to also depend on say if R is on layer 1, you need to know where you are with respect to the atoms on layer 2. So you have these new terms. Okay, now for interlayer hopping functions, you again, that's a little simpler, and so you can write this in this way, right? So I'm just reviewing. Here's our configuration dependent hopping functions, okay? And now if I want to define, now given a hopping function, right, in real space, then then if there was no relaxation, you would just do the block transform, and then you'd solve your problem. So I'm doing the block transform at each local configuration B. Here's the block transform. I can actually write it this way. Okay, so now what I have is block transforms, right? That depends on the local configuration. Okay, and I could similarly define these modified interlayer terms. Okay, so now if I want to go to, I want to transfer all this to momentum space and reciprocal space. What I need to do is this is the duality. Okay, it says to get the interlayer terms in momentum space. Now in momentum space, right? Okay, in momentum space, the block transform gives me B is depending on B and not Q. The role of the disregistry and momentum space is reversed. Okay. Now what's annoying here is you get a bunch of minus Q's and stuff. That's because the disregistry of layer 1 with respect to layer 2 is sort of like the disregistry of layer 2 with respect to layer 1. On the other hand, the wave numbers are kind of defined consistently. So it gets a bunch of minus signs. That really is just annoying. But anyway, so I could pretend they're not there, but they are there. Okay, so in the day, look, in the day we end up with a configuration-dependent reciprocal lattice Hamiltonian. Boom, that's it. This is it. Okay, so these G's are just giving you the local configuration of your, so if these weren't there, right, then literally you would have just the normal Hamiltonian, right, in terms of reciprocal lattice vectors. Okay, now, so now here, let me go back to the Okay, so I want to understand the effect of displacement on the band structure, local density of states, et cetera. So what we can prove is actually these, we can prove these results as a function of theta, right? This dysregistry goes like 1 over theta squared. Okay, so what that means is this is in configuration space. I'm looking at the displacement. So we see as the angle gets smaller and smaller, okay, what happens is, so if you have the angle, the width, your transition between AB and BA gets halved, okay? Whereas in real space, that says that the width is actually asymptotically constant, okay, where it's 5 atoms or whatever. So anyway, so we have control of, okay, and by the way, I was kind of fiddling about with this and this new, and so I looked at our paper. Where is that? Was that? No, that's, yeah, this came out of some archive paper, and the estimate we have there is not this, but this estimate falls pretty easily from it, but I didn't realize it at the time, but okay. So that's a nice estimate. And so, yes?
Is that still true if you take the width relative to the size of the domains? Or would it still go to 0?
Oh, no, here, okay, it's if you take the width relative to the size of the Moiré, then it is a unit, it is constant, yeah. So the idea is that basically you have like a, the kind of the boundary layer, right, is kind of, it scales like 1 over theta, okay? So so now here, I know I'm running super fast, but the bottom line is that if you look at our hopping functions, so this is just the real space hopping function. And so if G wasn't there, forget G first, this is just the real space hopping function. All G is the Fourier coefficient of the effect of dysregistry. And this just says that in fact, because in real space we have a sharpening, the effect of dysregistry, right? You need the Fourier coefficients don't decay fast, and so that means the rate of decay scales like theta. And then you do your duality, and more importantly, that tells us that the decay of the momentum space of the reciprocal lattice vectors actually scales like theta. So that means at small angle you're going to, and this is just the computation. This is here. This is probably the thing to look at. This is the AA. This is unrelaxed. This is your. And then here. Then this is the relaxed. This is your interlayer hopping function in the relaxed. So that means that you need larger. You need the G's have to be much larger to capture accuracy. So we have, now here I'm just going back here, just kind of a little bit reviewing the method. There's another parameter, so there's 2 parameters that come into this. One is, so you take so red is like your layer of interest, then you got to add but then you want to make some region in momentum space of R, size R, just to give yourself a buffer. Now that translates into some region of size R theta over here in reciprocal lattice space. Okay, so what you end up doing, what you do for each Q, you go and you generate your matrix, right, in terms of the G's, okay, and the G's are cut off by staying in this dark region, and then you have a cutoff in terms of the hopping length. Okay, so the simplest is just nearest neighbor hopping in momentum space, or you can go, say, next nearest neighbor, et cetera, et cetera. So there's 2 parameters, and okay, so again, bottom line is here's our Gaussian. In real space, our decay depended on the accuracy. It's no longer dependent on the accuracy when we go to this kind of more sophisticated momentum space method, but our rate of decay gamma, without relaxation, gamma actually scales like theta to the -1, theta to the 1/2. Okay, so as the angle gets small, the rate of decay actually gets faster and faster. Okay, whereas with relaxation, it's actually independent of the Moiré length scale, meaning that it's actually, as you might guess, it's actually much slower. Okay, and so so here's just some of our computations of band structure, and this just graphs of effect of again both these two parameters, R, the R region, which is the region of energy. You're sampling, as R gets large, you expect to have a more accurate method, and that's what we see. And this just shows the effect of R on the angle. And again, here you see that how in the unrelaxed case, you see that in fact, the rate of decay really gets fast at small angle, but it's pretty constant for the relaxed problem. And in terms of how large a hopping in momentum space, then okay, this is just the graph of that. Okay, so I think that's probably it. Okay, 3 minutes early, but nobody understood anything. But okay, thank you very much.